All right, well, happy Friday. Happy last May class for differential equations. The plan today is to continue talking about the Laplace transform. We'll do another example of using the Laplace transform to solve a differential equation, just so you can kind of get refreshed on the process. But then we'll start looking at how we can use this specifically when we have piecewise defined forcing functions. And we'll talk about why the Laplace transform might be nice as opposed to doing it the other way. Um, so yeah, so that's where we're going. Basically, we're just trying to expand our repertoire, right? But before I do that, let me turn it over to you guys. Any questions on homework or anything you'd like to look at that we've talked about so far?
Could we go over 7.2, number 6?
Absolutely. I'll put it on my list. Any others? No? All right. So let me go ahead and share my screen. We'll go take a look at that one. All right, so here's 7.2, number 6. It just says find the power series in X for the general solution. And what we'll do, we'll see if we can actually write that, like see a pattern and write it as a power series. If not, we'll just write out the first few terms of each one. And we'll just sort of see how that goes. All right, so let me go ahead and write this down. So we got the 1 plus x squared times y double prime plus 2xy prime plus 1/4 y equals 0. So this one's not an initial value problem. So that means we aren't going to know y0 or a0 and a1, right? Those are not going to be given to us this time, but we'll be able to still write this in terms of a0 times a bunch of stuff and then a1 times a bunch of stuff, right? So those are basically playing the roles of our c's. All right, so let me go ahead and put this sucker up here. So we've got 1 plus x squared times y double prime plus 2xy prime plus 1/4 y equals 0. All right, so since we weren't given an initial value, right? We weren't given initial values. We don't necessarily have a preferred center here. So we can actually center this wherever we want. I definitely have a preferred center. I don't know if it's the same one that you guys have, but I would recommend that we center this at 0 so that we use y equals sum from 0 to infinity of a sub n times x to the n. But that's not necessary. You can center it wherever you want. But this one, centering it at 0 is actually going to be much easier. I'm also looking at what I'm going to end up multiplying through. I'm multiplying through powers of x. Those are going to be easier to combine to things that are already x to the n. All right, so there's our y. So immediately, let's just go to our y prime, bump up the index by 1, and differentiate, and then do the same thing to get our double prime, 2 to the infinity, n times n minus 1, a sub n, x to the n minus 2. You do enough of these, this just becomes rote. You just start that way. You don't even consider doing anything. All right, so we're going to put those in here for our differential equation. So what I'm going to do is I'm going to go ahead and do the distribution when I put the sums in, just to save us that step. But basically, I'm just going to take those guys and put them up in here. So when I take 1 plus x squared times this, I'm actually going to get two sums. I'm going to get the sum that's written there from the 1 times it. But then I'm going to get another one when I distribute the x squared in. And that's going to be, again, from 2 to infinity, n times n minus 1 times a sub n times x to the n. Because the x squared times x to the n minus 2 brings me to x to the n. So there are those two pieces. The next one When I multiply by 2x, this will be from 1 to infinity, we'll have 2n a sub n, and then x to the n, because again, x times x to the n minus 1 brings me x to the n. And then lastly, we've got the sum from 0 to infinity of 1/4 a sub n x to the n, and then that all equals 0. All right, so give me some confirmation here, thumbs up, or say, yep, we're all good. Are we good at this point?
Yeah, looks good.
All right, so far so good?
Yeah.
All right. So now that we're here, the next goal is to make it so that all of the powers on x are the same. And I'm going to target x to the n because I already have these three all as x to the n, which means I need to change this one by adding 2 everywhere there's an n in here. So I'm going to change colors just to illustrate that this is the one that I'm changing here. So I'm going to get n plus 2 times n plus 1 times a sub n plus 2 times x to the n. So I'm shifting it 2, so n plus 2. And then because I'm shifting it 2, I have to change my initial start. And this one, we actually go the other direction. We subtract 2. So the first sum here is the same as what I just wrote in red. Excuse me. And you can pretty easily check that just by plugging in a few n's here, and you'll see that they're the same things that you get up here when you plug in some n's. But now we're such that everything is x to the n. All right, so are we good with that switch? Questions on that? Because that's another thing that we do all the time with these. Okay, so now I'm going to put this all together into one sum. I'm going to get n plus 2 times n plus 1 times a sub n plus 2 plus n times n minus 1 times a sub n plus 2n a sub n plus 1/4 a sub n. And all of that is being multiplied to x to the n. So I'm literally just taking those pieces and sticking them together, but with the new guy. But this one's actually going to go from 2 to infinity, because I don't actually get all of the pieces until I get to n equals 2. Right? When we're at n equals 0, we're only getting the first and the last one. When we're at n equal 1, we're getting the first and the last 2. It's at n equal 2, I finally get all 4 of them. So that's why I've got this n equal 2. And that's also why I put this little plus here, because I need to see what I get when I plug in 0 and I plug in 1. So when I plug in 0, this thing is going to give me 2a sub 2. This one's going to give me 1/4 a sub 0. And so those are the pieces from n equals 0. Then I need to do the same thing, but for n equal 1. Well, that's going to give me 3 times 2, which is 6 a sub 3. This one's going to give me 2 a sub 1. This is going to give me a 1/4 a sub 1. So I'm just going to go and write that as 9/4 a sub 1. And that's going to be times x. Right? Because when n is equal to 1, these things are all x to the first. Whew. All right, so how are we doing? Are you still with me? What questions can I answer at this point?
So I just want to be sure that all this is being added. So we plugged in 0 and 1 and got those. We're
Yep,
still adding it to our sum.
exactly. So
Okay.
here's the first parentheses, that's our 0,
Mhm.
plus second parentheses, that's our 1, plus the sum going forward. All right, so now we're ready to start trying to figure out our a values. So from the first piece here, we've got a2 is going to equal minus 1/8 a naught. This has to equal 0, right? Remember, our target is 0. So this parenthesis stuff holds the constant term. So for that to equal 0, a2 has to equal minus 1/8 a naught. We can do something similar with this one. We need to get 0x. So if we take 6a3 plus 9 fourths a1 and set that equal to 0, we're going to get minus 3/8 a1. All right, so that's cool. A0 and A1 are free choices, but once we make those choices, we know what A2 and A3 are. But then going forward, we're going to use this thing. And I'm going to leave it with n's. I'm not going to plug in specific numbers. I want to have it as just as a recursive formula so that we can just continue to plug in the next n, plug in the next n, plug in the next n, and so on. So this one, we're going to get n plus 2 times n plus 1, a sub n plus 2. I'm going to go ahead and combine all these because they're all a sub n's. So I'm going to get n squared plus n plus 1/4 times a sub n. It's just plus n because when I distribute here, I get a minus n to go with this plus 2n. But again, I know that needs to equal 0. So a sub n plus 2 is going to equal negative n squared plus n plus 1/4 divided by n plus 2 times n plus 1 times a sub n. All right, so are we good with that recursive piece? All right, so here we go. Let's get other ones then. So a sub 4, if we use this formula, we're going to let n equal 2, right, to get 4. So we're going to get 4 plus 2 plus a fourth. So that's 25 fourths divided by 4 times 3. And so I'm pretty sure that's minus 25/48. Oops. Times a2. Well, a2 was minus 1/8 a naught. So that's going to turn this into 25 over, let's see, 64, 384, I think, a naught. So there's a4 in terms of a naught. So then a5, we're going to plug in 3. 9 plus 3 is 12, and a quarter is 49 fourths. Put a 3 down here. We got 5 times 4 is 20. So that's 49/80, I believe. So negative 49/80. Definitely check my arithmetic there. But that's going to be negative 49/80 times a3. All right, well, A3 is minus 3/8 A1. So when we multiply that together, that's going to give us 147 640th A1. And I'm actually going to stop here, but you could continue, right? To get the 6, you plug in 4. A sub 6 is going to be in terms of A4, so you put that in, get your number, and so on. But here's how this is playing out now. This is what our solution looks like. It's going to be A0. Okay, that's free choice. Plus A1 times X, because A1 is a free choice. But then we're going to get negative 1/8 A0 X squared. Our A2 is negative 1/8 A0, and A2 goes with X squared. Then we get minus 3/8 A1 X cubed plus 25 3/84 X A0. Second here. So 25 A0 X to the 4th plus 147 640th A1 times X to the 5th plus dot dot dot. So there are the first 6 terms for this thing. And we can actually separate this if we want into the 2 different pieces. A0 is going to be times 1 minus 1/8 X squared plus 25 3/84 X to the 4th plus dot dot dot. And then the A1 is going to be times X minus 3/8 X cubed plus 147 640th X to the 5th plus dot dot dot. All right, so they didn't tell us to go to a specific number of places. I also do not see a pattern here. There might be one, but I definitely don't see it. So I'm good. Like on an exam, for example, on your exam next week, because our next exam is a week from today, and there will be series stuff on there. So like if you got it to this point, I'd be more than happy. I'd be like, all right, yep, you're definitely getting it. That's what this thing looks like. Anyway, so the A0 and A1, hopefully you remember that those are from our initial conditions. So if we were given initial values, we just fire those in for A1, A0 and A1, and we're good to go. All right, so was that a good little review for the process here?
Yeah, it just bothers me how easy it is to make a little mistake with these sort of things.
Yep. And you make a mistake early on, and it just like gets bigger and bigger and worse and worse and worse, right? The whole throwing gasoline on the fire kind of thing. So for these, definitely slow and steady. Slow and steady. But just remember, I mean, there's a process, right? You start with just like I had here in the green, your y. So you know your y prime and your y double prime. And if you center it somewhere else, the only thing that changes is you have x minus c to the powers instead of just x. Then put it back in a differential equation, bring anything in. But then you need to make sure that everything is at the same power. And I highly recommend getting them so that they're all x to the n. Then strip out anything from the ones that start with lower counts, right? Like in this case, we had to get the zeros and the ones. And then you can put them together. And then once it's together, create your recursive formula, deal with whatever the first things are. And then to start going through the motion. All right. Anyway, there you go. So other questions on this one? How are we feeling about it?
Do you mind going over again your I don't want to call it a transformation, but our first sum, turning it into an x to the n?
This one where I got the
Yeah.
red? Yeah.
Yeah.
Yep, totally. So let me show you a way to kind of do that with substitution, because I think sometimes when you use the same letter, I think sometimes it's hard to kind of see how everything matches up. But let me show you how, like with a substitution, this plays out. So basically, here's what I want. From here, I want n minus 2 to equal u, right? I just want that x to the u. So that tells me that n is going to equal u plus 2. So in my sum, what I can do is replace all of those n's with u plus 2. So I get u plus 2, u plus 2 minus 1, a sub u plus 2, x to the u plus 2 minus 2. And then for my start value, remember what we needed was n equal 2. Well, if I plug 2 in for n, 2 minus 2 is 0. So that means I'm going to start at u equals 0. So if you kind of just simplify all this, now it looks like u equals 0 to infinity, u plus 2, u plus 1, a sub u plus 2, x to the u. And then just change all those u's back to an n, because the name of that doesn't really matter. And you see that that's exactly what I've got in red.
That definitely makes way more sense looking at it that way.
Yeah. So if that helps, do it. I'm just a big fan of the I need to shift it by 2. I need this to go up by 2. So I'm going to make all these things increase by 2. N plus 2, n plus 1, n plus 2, n.
Yeah,
And then
saying it like that helps too. I like both.
and then I just know that my count has to go the opposite direction. So anyway. And I would say that that's one of the more difficult steps, actually. Like as when you're starting out. Like honestly, for me, that's not a hard step. For me, all the work is actually down here in the recursive thing. That's where the majority of my time is spent. But when you're first learning how to do this shifting of your index is challenging, but super important. You got to get that down, because otherwise you can't even get to this recursive definition. All right, cool, good question. Other questions? Let's see here. So Victor just said, put in the chat box, number 16 is confusing. What changes when it's not centered at 0? Okay, we'll go look at that. Let's go look at that in a second. But any other questions on this one in particular? Okay, so it's not sounding like it. So let's go look at number 16. We'll go back to the book here. Try that again. There we go. Okay, so 16, this one says find the power series where we're centered at 3. Let me write down the formula here. We got y double prime minus y equals 0. All right, now we're going to center it at 3. I'll go back to the whiteboard. And let me...
I have a quick question for you.
Yeah, sure.
So suppose if the problem we just didn't have, polynomials, suppose it was, trig functions. Where you started your sums, like your power series, would it still be the same as what you have written in the green in the left?
Yes.
Okay.
I would still start with this because this is the generic power series for my function.
Hmm.
Before I go to 16, let me show you exactly what I would do in that case. So I'm going to change this just real quick to, like, instead of 1 plus x squared, let's say instead we had a say sine of x times, right? That's kind of what you're
Yeah, exactly.
shooting for.
Something like that. Yeah.
Okay. So I would actually start exactly the same way with my y's. So my y is a to the an x to the n, get the derivatives. And then when I go back and I punch it in to multiply, like the last ones are going to be the same. The last two here are going to be the same because they came from the 2x and the 1/4. But what would change here, let's erase this for a second. I would now have to take the power series for sine. You guys remember the power series for sine? It's okay if you say no.
I want to, but I don't.
So sine, sine of x is the one that goes x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. You get the odd powers of x. It's the sum of x to the 2n plus 1 over 2n plus 1 factorial, starting at 0. And then we need minus 1 to the n to get the alternating. Anyway, that's the power series for sine. So what we would do is we would actually multiply those two power series together. But that's actually kind of tricky, because basically the way that you tackle this, I'm just going to take the first couple of sine, and then we're going to multiply that to the first couple of this one. So think about what we get. We start with 2. You get 2 times 1, so 2 a sub 2 times x to the 0. And then we're going to get plus 6 a sub 3 x plus 12 a sub 4 x squared plus so on and so forth, right? And then we'd have to FOIL. And the issue here is, like, you're doing basically infinite FOIL, right? Because these polynomials go forever. But what you could do is just start thinking about multiplying them out and grouping like terms. Like, to get x's, I'm only going to get x's from 2a squared times x. So this will give me, or 2a2 times x. To get x squareds, well, that's going to come from 6a3x times x. So we'll get plus 6a3x squared. For the cubes, now this gets a little tricky because I can get cubes from the 2a squared times this x cubed, and also the 12a4 times x squared times x. So that's going to give me 12a sub 4 minus 1 x cubed. That looked like an a sub 4. So where those are coming from, the 12a sub 4 is that product. And then when I take, oh, it should be over 3, minus 1/3. 2a2, gosh darn it, I'm getting all kinds of things in there. 1/3 a2. That one's coming from multiplying those two together. So 3 factorial is a 6th times 2 is a 3rd. So we get that. And then you just keep going, and basically you go as far as you need, depending on what we're actually doing here, like how many terms you want for each of your fundamental set. So this gets to be way more challenging when you have to bring in power series for other stuff, which is why all the ones you ever see in your homeworks are going to be just multiplying by polynomials. But yeah, so that's the process on that. So then we get that sum, and now we'd have to add it to these sums. And they tend, when you have these, you tend not to get nice recursive definitions. So it's definitely more of a slugfest. You just get in and you just got to keep moving, keep pushing towards the final answer there. Anyway, does that kind of make sense, Bradley?
Yes, that makes sense.
And it probably should also show you why I would never do that to you, because I mean, this stuff's boring and tedious enough, right? But this is the kind of thing computers love doing. Computers going to have no problem with this. You can program into it the power series for sine and cosine and e and all the other things, natural log, whatever, and then it'll just, it'll keep multiplying all day long until you tell it to stop. All right. So let's go look at number 16 then, the one that Victor was asking about. Clear this. And so that one was y double prime minus y equals 0. But this time they said, let's center it at 3. Okay, so this is what we're going to do now. We're still going to go with the sum from 0 to infinity. But now it's going to be a sub n times x minus 3 to the n. So when you have a different center, you just automatically start with a different y. But then from here, it's the same thing as before. We differentiate this thing, so we get n a sub n x minus 3 to the n minus 1. You do have to worry about chain rule, but x minus 3's derivative is 1, so we don't actually, nothing happens there. And then y double prime, whoops, that should be a n equal 1, sorry. This guy's n equal 2 to infinity, n times n minus 1, a sub n, x minus 3 to the n minus 2. So notice that really the only thing that changed was instead of having x to the powers, we have x minus 3 to the powers. All right. But then at this point, it's business as usual. We'll plug those things in. So we got the sum from 2 to infinity of n times n minus 1 a sub n times x minus 3 to the n minus 2 minus the original one. So 0 to infinity, a sub n x minus 3 to the n. And now let's change our count. So again, I want this to be x minus 3 to the n. So I need to change everything by 2. So it's going to be n plus 2 times n plus 1 times a sub n plus 1, or sorry, plus 2 times x minus 3 to the n. But my start now, instead of being 2, is 0. All right, so they both match ends, and even better, they both match starting values. So this is really nice. It means I can just take them as they are and put them together. So n plus 2 times n plus 1 times a sub n plus 2 minus a sub n times x minus 3 to the n. And again, like before, we need this to equal 0. So that's going to give me the recursive relationship a sub n plus 2 is going to equal 1 over n plus 2 times n plus 1 times a sub n. And now we're ready to go. A0 is going to be A0, A1 is going to be A1, A2, well, that's going to be whatever we get when we plug in 0 into that. A3 is going to be what we get when we plug 1 into that, and so on and so forth. So, Victor, I know you say that it's confusing because it's centered somewhere other than 0. Don't let it confuse you because it doesn't really change anything. The process is identical. It's the same steps. We just now have x minus our center raised to the power. So is that better for 16?
Yeah,
Yeah.
I think I did something wrong, but yeah, not sure what.
Okay. Well, hopefully you can go
Probably
back
a
and find
derivative.
possibly. Yeah. So go back and see if you can find it. But again, don't let it throw you. If you're centered somewhere else, it's business like usual. All right. So we good?
And what it means, how you present the answer here.
Oh,
You need a naught or a one or
okay. So it's going to be kind of like that other one. I'll go ahead. Let me just finish this guy off. We'll come back to it. All right. So here's the deal. So A naught is A naught. It's whatever it is. So and A1 is A1. A2, if I plug in 0, I get that's equal to 1/2 A sub 0. A3, I'm going to plug in 1. So I get 1/6 A sub 1. I'll go get 2 more. So then A4, if I plug in 2, that's going to be 1/12 A sub 2, which means this is 1/24 A sub 0. And then A5, when we plug in 3, that's going to give us 1/20 A sub 3. Well, A sub 3 was 1/6, so this is 1/20 A sub 1. So now let's start putting this back into what y is going to look like. Let me clear some space here real quick.
yeah, now we make.
Now you're good?
Yeah.
Yeah. Okay. So this will be y equals a naught plus a1x plus 1/2 a naught x squared plus 1/6 a1 x cubed plus 1/24 a naught x to the 4th plus 1/20 a1 x to the 5th plus plus. Oh shoot. Hold on a second. I don't have this quite right. Should be a naught plus a1 times x minus 3 plus 1/2 a naught x minus 3 squared plus 1/6 a1 x minus 3 cubed, and so on down the line. I forgot that we were centering it at minus 3. So I'm going to separate it into the two pieces. So with the a naught, we get 1 plus 1/2 times x minus 3 squared plus 1/24 x minus 3 to the 4th plus dot, 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 dot. And then a1 is going to be times x minus 3 plus 1/6 x minus 3 cubed plus 1/20 x minus 3 to the 5th plus dot, 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 dot. That shouldn't be an equals, that should be a plus. But this one, I'm even going to take it one step further because I can write these as sums. I see a pattern. I've got x minus 3 to the 2n, just getting evens. And it's going to be over 2n factorial. It's 2 factorial, 4 factorial, and so on. And this, I believe, starts at 0. And then the next one's going to be a sub 1 times. This time I'm going to get x minus 3 to the 2n plus 1. And again, over 2n plus 1 factorial. And again, start this count at 0. And I think we're good. So we're even able to go one step further and find the power series for those. And then maybe we can even figure out what functions give us those power series. But we'll go ahead and leave it as it is. Anyway, so better, good.
Yeah, it makes sense.
Okay.
And I think the process is straightforward when you memorize like derivatives, I guess.
Yeah, it
Just
is.
for
It's
everything different than x to the power, it will be hard.
yeah. Yeah, it adds one more thing you have to pay attention to. And you saw that even I made that mistake, right? Like when I started writing it out, I immediately went to the x's. It's like, no. It's actually the x minus 3s. I know that's an error I make all the time because I always default, like my choice, if I can choose, my choice is always center at 0. So I just get in the habit of it's just x to the n. And I forget when we center somewhere else to put that in. All right. So cool. Cool. All right. So that's a good little review of how to do the power series. And this is actually really good justification for having Laplace transforms, because if we can develop another method that works that doesn't involve power series, yes, please. Right? Power series are long, cumbersome, lots of places to make mistakes, very tedious, not fun at all, right? They work. That's the beauty of power series, is they work. But if we can have other things, we want them. And so that's what the Laplace transform is good for, right? It actually just gives us another way of doing this that doesn't require calculus. Honestly, it doesn't even require power series. So I want to remind you about how that works. I'm going to pull up, just do an example here on the board. Go ahead and clear all this stuff. And just to kind of refresh your memory with Laplace transforms, let's say we're going to try to find the solution to y double prime plus y equals the sine of 2t. And like before, I'm going to give you initial conditions. So y of 0 equals 2, and y prime of 0 equals 1. So this is another one that you can do, that you know how to do, that you know how to find the solutions for. For the homogeneous part, it's a matter of creating the polynomials, doing your thing. And then for the non-homogeneous part, this is one where you would do undetermined coefficients. You make a guess involving sine of 2t and cosine of 2t, and work your way down. So we definitely have a way of doing it, but instead, let's use the Laplace transform. So like we discussed last time, the Laplace transform, you can take the Laplace transform of each side. It is a linear operator. So that means like here on the left, this is going to be the same as the Laplace transform of y double prime plus the Laplace transform of y. So we can actually split that up. Now, if we wanted to, we could go to the definition and calculate the Laplace transform. Just to remind you how that works, the Laplace transform of f of t, it is the integral from 0 to infinity of e to the minus st times f of t. Right, but we're gonna save ourselves a little bit by using the fact that these are already all been figured out. Like the Laplace transform of pretty much every function has been determined. And like I showed you last time, there's that sheet. It's one of the files in Canvas for you. That was all the Laplace transforms for all those functions. So feel free to use that. 100%. Feel free to use that anytime you're taking Laplace transforms, because that's going to help us a bit.
If we could see this, will look like a change of coordinates or something like that. That
Kind
transformation.
of. Yeah, it's going to turn it into S's instead of T's. So, for example, actually, let me give me 1 second here. I'm going to stop sharing so I can get all this crap off my screen. I'm going to go find the Laplace transform sheet that I had here somewhere. Okay, and now let me go ahead and share my screen to it. Okay, so I gave you this in the Canvas page. If you look under the files, you'll see this. But these are the Laplace transforms for different functions. So basically, what we're doing is we're going from the t world to a world of s. So it is a change. It is a transformation to a different coordinate system. But it's done in this very specific way where we integrate e to the minus st times our function. So did I answer that question, Victor? I think I did, but I don't.
Yeah.
I'm not sure. Okay. All right. So think about what we were doing. We had, for example, the sine of 2t. So that's this form right here, where a was equal to 2. So if I put that in right here, I'm going to go ahead and switch back, go over to the whiteboard again. This guy on the right is going to be 2 over s squared plus 4. So it was a over s squared plus a squared. So that's the Laplace transform of sine of 2t. The Laplace transform of y, we'll go ahead and keep that. Laplace transform of y. But now let's go find the Laplace transform of y double prime. So we'll go back to that table. And if we go down a little bit, we can see it's right here. Change colors. So there's y double prime. I call it f prime. But here is what that is going to be. Now, notice it still has the f of 0. Okay, well, an f prime of 0. So that's going to be y of 0 and y prime of 0. But then it's got this big F of s, and that notation, this bit right here, that's the Laplace transform of f. Okay, that's the notation that we use here when we want the Laplace transform of f. We go to big F of s. Okay, so I'm going to go back and put that in. So again, with that, the derivative there, we saw that we had s squared times the Laplace transform of y minus s times y of 0, or sorry, y prime of 0 minus y of 0. Make some more space there. Okay, so let me just bounce back here one more time so you can see it. Oh, I did have those right the first time, I'm sorry. So s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. All right, so what this is going to let us do now is solve for the Laplace transform of y. So let me put in my numbers here. So we're going to get s squared plus 1 times the Laplace transform of y. I just group those. Minus 2s minus 1 equals 2 over s squared plus 4. So I'm going to solve this for the Laplace transform of y. So I'll add 1 and 2s to the other side. And then I'm going to divide by s squared plus 1. So I get the Laplace transform here is going to equal, I'm going to go ahead and combine this into one thing by getting a common denominator. So we're going to get 2s cubed plus s squared plus 8s plus 6 over s squared plus 4 times s squared plus 1. I'm just double checking my algebra there, but I think that's right. Okay, so right now, I know we're just sort of still in the middle of this, and it's like, okay, whatever we're doing here. But basically, what we now know is, I don't know why yet, right? I don't know why yet, but I do know what its Laplace transform looks like. So now what I want to do is I want to go backwards. I want to go back to that chart, and I want to look on the right-hand side and see if we have this form and if we can backtrack. Now, I'll tell you right now, you're not going to see this form. In fact, let me go back over there, kind of remember what we got here, right? If I go back and you look on the right-hand sides, we don't have anything that has on the bottom two sums of squares being multiplied unless they're exactly the same thing, right? But we don't have that. So the form we have isn't on our chart, but we're going to be able to get to it by breaking it apart.
I have a quick question.
Yeah, go for it.
Do we focus on the denominator, or do we take both numerator and denominator into consideration?
You're going to need to take both into consideration.
Okay.
I tend to use the denominators as the first kind of way to start breaking it up. For example, like let's say we had s squared minus a squared on the bottom. I know then, oh, it's going to be one of these two forms. And then I look at the top to see which of those two forms it is. Because if you use the top, look at how many tops have just a number. Here's one, here's one, here's one, there's one, right? So if you just look at the top, it doesn't really help you differentiate down to which type it is. So I key in on denominator first. But yes, you do need to take the whole thing into consideration. Okay, so what we're going to do now is some algebra. We're going to break this sucker up. We're going to do partial fractions. So we're going to want something over s squared plus 4 and something over s squared plus 1. And this first one, it's going to have to be linear on top. And the same thing with the second one, it's going to be linear on top as well. So hopefully you remember with partial fractions, if you've got a quadratic factor on the bottom, you have to put a linear on top. If it's a linear factor on the bottom, you put a constant on top. Okay, so then if you get a common denominator, as plus b times s squared plus 1 plus cs plus d times s squared plus 4. And that's the top. What we know is that that has to equal this thing over here. So let's group this by powers of s. So s cubes, I'm going to get a s cubed plus c s cubed. For the s squareds, I'm going to get b and d. So plus b plus d s squared. For the s's, I'm going to get as plus 4cs. So I'm going to get a plus 4c times s. And then for my constants, I'm going to get b plus 4d. So now I can create a system of equations. Coming back to this, I've got a plus c has to equal 2, because it was 2s cubed. B plus d has to equal 1, because it's 1s squared. A plus 4c has to equal 8, and then b plus 4d has to equal 6. All right, so now we get to solve. Well, these two, when I combine those, I'm going to get a equals 0 and c equals 2. If I just subtract the top one from the bottom one, that'll give me c equals 2, and then plugging that in gives me a equals 0. This one, if I do the same thing, if I subtract the top from the bottom, that's going to give me d equals 5/3, and then b equals minus 2/3. All right, so basically we did all that work to find out that this Laplace transform can be written instead as, all right, well, as plus b, that's just b, so we're going to get minus 2/3 times 1 over s squared plus 4. We have cs plus d. I'm going to split it into two pieces. So I'm going to get plus 2s over s squared plus 1. That's the c times s. Plus d, so 5/3 times 1 over s squared plus 1. And now this is what we're going to go search for the forms. We're not going to be concerned with the numbers out front, because since this is a linear operator, those constant coefficients are just going to kind of stay there. But let's go look for these forms. So we got 1 over s squared plus 4, 1 over s squared plus 1, and s over s squared plus 1. Before I jump to the other page to go back and look at the Laplace transforms, are you guys okay with where this came from? I'm not saying that you like partial fractions or it was fun, but you see the process. You remember the process? Thumbs up.
I don't like partial fractions.
No, nobody likes partial fractions. Oh, that's not true. There are some people who like partial fractions, but they are very, very odd and strange individuals.
Well, I mean, I like partial fractions more than power series, not gonna lie.
Okay. But does that mean that you like partial fractions?
Not at all.
Okay, so there you go. I mean, yeah, I mean, ooh, I like the Red Sox more than I like the Yankees. Okay, I dislike both of them, right? But there are levels of dislike. That was for Bradley's sake, by the way. He totally understands that reference. All right, so let's go back to power series. So remember what we're looking for. 1 over s squared plus 1, 1 over s squared plus 4, and s over s squared plus 1. Okay, so we need a sum of squares, not a difference of squares. So let's see if we can kind of go up here a little bit more. Oh, hey, here we go. So we had s squared plus 1 and s squared plus 4. So those are definitely coming from sine. Just one of them is going to be a equals 1. The other is going to be a equals 2. So we're going to get sine of t and sine of 2t in some combination there. The other one was s over s squared plus 1, which if we just look over here, came from a cosine. All right, so here's what we get to do. If we go back, now I'm ready to tell you what y is. All right, so I'm just going to kind of start here at the end. So I've got 5/3 times, well, 1 over s squared plus 1, that was a over s squared plus a squared. That was the sine of 1t. The next one, the 2, goes there. S over s squared plus 1, that was the cosine of 1t. And then this one, with the 1 over s squared plus 4, the form was a over s squared plus a squared. So I'm actually going to bring that 2 in here so that it looks exactly like what I want. And that gives me then minus 1/3 sine of 2t. And we can put a box around this. And there's the answer. There's the solution to this initial value problem. It's exactly what you would have found if you had done it the old-fashioned way. Find your solution to the homogeneous. Well, that pair was going to be sine of t and cosine of t. So you're going to get c1 sine t plus c2 cosine t. Then find a solution to the particular. Well, since we've got a sine of 2t, we're going to guess the form a sine of 2t plus b cosine of 2t. Put that into the derivatives in a differential equation, solve that system, blah, blah, blah. You're going to end up with, okay, we have minus 1/3 sine of 2t and no cosine of t. Then you'd have to use your initial conditions. You're going to plug in 0, set it equal to 2. You're going to take the derivative, plug in 0, set it equal to 1. That's going to lead to those 5/3 for the sine of t and the 2 for the cosine of t. So we would have gotten to exactly the same place, just through a very different method. And like I mentioned last time, the trade-off here is we went from calculus world to algebra world. We didn't do a touch of calculus here. But anyway, go ahead, Bradley. You were about to say something.
Do these require initial values?
They do not. If you don't have initial conditions, remember where we plugged that in when we were over here?
Yeah.
We had the y of 0, y prime of 0.
Mm-hmm.
Those would just stay as y of 0, y prime of 0. And when you do this, like all the algebra and partial fraction stuff, you're going to get those as multiples of these things. So like there would still be instead of a minus 2/3 of this, it would have been like a 2. No, that would have been over here for these guys. You would have ended up having some a naughts and a1s, or some y of 0 and y prime of 0s still in here. And that would have led to C1 and C2 kind of ideas.
Got it.
Okay, so without the initial conditions, they would have stuck around. Usually, if you don't have initial conditions, you don't go to Laplace transforms. I mean, you can, it's fine. It's just Laplace transforms are most beneficial when you have the initial conditions. So you can plug in those numbers like we did over here, which then leads to your particular, your specific solution for that initial value problem.
Makes sense.
All right, so there's a little bit of a review on the process and why we care about this. And the beautiful thing about Laplace transforms, honestly, is that it also applies to things that are not second order. You could do this for a 10th order differential equation. It also doesn't matter what kind of coefficients you have. It doesn't matter, any of that stuff, because you can take the Laplace transforms, but as long as you follow the rules of linear operators, you can do Laplace transforms all day long. Right. So it's actually a really nice, viable method for solving initial value problems when if you don't want to do calculus. But I know for most of us, calculus isn't the problem, right? The algebra, like this is pretty algebra intensive, and there's a lot of stuff you can mess up and a lot of things you have to do. But again, just think like honestly, in reality, algebra is easier. It's easier stuff to do. There's more we have to remember probably, but it is easier. And as this was getting developed, man, can you imagine if you're an old-timey mathematician? Go back a couple hundred years when we didn't have this lovely technology that would just do it for us. Oh, this was a godsend. This was an absolute godsend.
Where would be a good place to review linear operators?
Linear algebra somewhere. I don't know if anybody who was in that class kind of remembers a chapter or anything where you kind of ran into that. Linear transformations, linear operators, they're all kind of, it's the same kind of idea. So in your linear book somewhere you can find it.
So I guess it was just the terminology. A linear operator is the same as a linear transformation.
Yeah, so a linear operator is an operation that does linear transformations.
Okay.
Yeah. All right. Now, with that said, you might still be going, yeah, but I don't need to trade the algebra for the calculus. I like the other method. It works for me. I don't see any reason why I need to go back to this new thing. Like, can't we just do what we did before? Okay, well, the answer to that is, of course, that's fine. You want to do it that way, have at it. But there are real situations where having the ability to do the Laplace transform is super beneficial. And let me just give you an example. At least this isn't necessarily coming from a specific thing, but there are plenty of specific things that do this kind of stuff. But like, let's just say, for example, I want you to solve this differential equation. So let's go to say y double prime plus 2y prime plus 2y equals, I'm going to put here f of t. But what I'm going to tell you about f of t is that it starts as t, then it turns into sine of t, and then it turns into 0. And let's just say that it's t until we get to pi, and then it's sine of t from pi to 2 pi, and then starting at 2 pi, it's 0 again. All right, so you see this problem. And let's just think about what we would have to do to solve it. If it wasn't piecewise, no problem, right? If it wasn't piecewise, you have y double prime plus 2y prime plus 2y equals t. You're good to go. If it was just equal to sine, you're good to go. If it was just equal to 0, oh yeah, you're super happy. That's homogeneous, so we're definitely good to go. right? So you would know what to do if it was just any one of those at any point in time.
Real quick before
Uh-huh.
we get into it, would it be possible, like just looking at this right now, would it be possible to solve for each one and then set them up as a linear combination?
Okay. I like how you're thinking, Bradley, because that's what we would have to do. We would have to solve them individually, and then we'd have to basically put them together. And specifically, let's say that this was an initial value problem. All right. So let's just say that f of 0 was 1, or y, not f of 0. Hold on. Scratch that. Let's say y of 0 was 1 and y prime of 0 was 2. Right. So we got initial conditions. So think about what we could do. We could start by solving this one with the initial conditions as presented, right? And we solve this and we get y equals whatever, blah. Because we would get a solution to it, right? We would get a particular solution because we have initial values. So we have y equals. All right, then we would turn our attention to the next one. Let me actually, instead of calling this blah, even though that's fun, let me call it, say, f of t, little f of t, just for a name. Okay, so we get y is equal to some function of t. Well, if you think about this one, we need some initial conditions if we actually want to get the solution. Well, the initial conditions for this would be the ending conditions for the first one. So we would need y of pi to equal f of pi. And we would need y prime of pi to equal f prime of pi. So whatever came out of this first one, we would have to make it so that it connects up to the second one.
We would just need to plug in pi, differentiate it, and then plug in pi again.
Yeah, to whatever this solution was. And then those are our initial conditions that we would use to get a solution to the second one. So let's say that that gave us g of t. Okay, so this was step 1. Brings us over here to step 2, which then is going to bring us up here to step 3, which would be, okay, well, now we're going to go to the y double prime plus 2y prime plus 2y equals 0, but its initial conditions are going to be y of 2 pi equals g of 2 pi, this thing, and y prime of 2 pi is going to equal g prime of 2 pi. So this is what we would have to do if we were going to do it kind of the old school way. We'd have to break it into 3 pieces, and that's kind of like what you were saying, Bradley, is go, okay, let's solve each one separately. But we're not exactly making it a linear combination of them. We're just connecting them together. We're taking those pieces and linking them so that we get a continuous function and a continuous smooth function.
So we would add all the solutions together?
No, it would end up being your answer would be a piecewise thing.
Oh, okay, that makes sense.
It would be f of t when t is less than pi, g of t when we're between pi and 2 pi, and then let's say the solution to this was y equals h of t. Okay, so our solution would end up being piecewise itself. We'd have all those different pieces like that. All right, now in the real world, you can probably see where this comes up. Like, let's take a really easy example of one of the things that we were talking about before. Think about the circuits. Remember the LRC circuits? suppose it's, all right, nothing's going on. It's just not plugged in or, not turned on. So we're at 0. Then we, it's plugged into the wall. We throw the switch. All right, so now there's a sinusoidal driving function. And then we turn it off again. Well, now it's back to 0. So that one would have been a from 0 to sine back to 0. But it would require that same kind of thing where we have to link these together. And out in the real world, we often have way more than just 3 pieces. I mean, think about all the things out there that we try to describe mathematically and how many different kinds of forcing functions there might be, right? It's pretty gnarly. Well, I'm just going to tell you right now that Laplace transforms make this kind of thing way easier. Like way, way easier. But to do that, I have to introduce you to a new function. And this function is called the Heaviside function. But we're going to use it to help us deal with this piecewise stuff. So we can write this piecewise thing as just one expression that we can then take the Laplace transform for. All right, well, so that's the why we're going to care about this, is this kind of thing. So let me first just introduce you to this guy called the Heaviside function.
I think this is the first new function I've learned since hyperbolic trig.
Yeah, it probably has been a while. No doubt about it. All right. Well, so get excited, right? It's like, yes, finally something new. All right, so
what was it called? The fucking we just went over it. It had like a W for its symbol, and it like
the Wronskian.
Yeah, Wronskian. Yeah.
All right. Yeah. So the Wronskian. Yeah, that's true. That was even though, but the Wronskian isn't actually. Well, it is a function, but it's not like it's a specific like class of function, right? It's the result of doing a process. So yeah, so that was new. But it has been a while, right, since you've actually learned a new function like exponent or log or anything like that. Now the Heaviside function, it's going to be written as like this. So it's u sub c. So you see the u sub c. That's going to tell you this is Heaviside. And the way that the Heaviside works is it is a piecewise defined function that's either 0 or 1. And it's 0 when t is less than c, and it's 1 when t is greater than or equal to c.
I like it.
Yeah, it actually is a pretty nice function. It goes by a different name often, and I'll tell you that name in a second. But let's start by drawing its graph. Okay, so let's go ahead and draw the graph of this thing. So somewhere out here is going to be the c that we pick for our Heaviside. So we're going to get 0 when we're less than c, 0 when we're less than c, and then we get 1 when we're at c or further on. Ta-da! All right, so there's the Heaviside function. Another name that this is also called a step function. So you'll see that when you're reading, they'll often talk about step function. And I think in this book, I think they call it the step function, the unit step function, actually. Yeah, I just checked, look back real quick in the book. But they call it, that's the book negotiation is, they call it this the unit step function. And it's called the unit step function because we're going up 1 unit. Now, what I like to think of this as, I think of this as a switch. It starts off and then turns on. So when you have the Heaviside function, it really is, it's just going to say, hey, turn this thing on at c equals whatever. All right. Now, what this has to do with piecewise functions is this. Imagine I told you here's a function. F of t equals u sub 2 of t times t cubed. So u sub 2, come back over here. So that's c equals 2. So that tells me that this is equal to 0 until we get to 2. And then once I get to 2, this piece is equal to 1. Well, we could instead write this as a piecewise function. Well, it was 0 until we got to 2. And then once we get to 2, this becomes 1. So we get 1 times t cubed, which is t cubed. So multiplying by the Heaviside function will make it the same as turning on that function, turning on the other function. So that's why I think of this as a switch. So as soon as I see this, u sub 2 times t, of t times t cubed, that tells me t cubed is doing nothing until we hit 2. And as soon as we hit 2, t cubed turns on. All right, so when you have a piecewise function, you can actually get it so that you can write it as a series of Heaviside functions instead of piecewise. Now, this is how you turn it on, right? A Heaviside turns things on. So let's think about what you would have to do to turn it off. Like, what if instead I wanted the piecewise function t cubed until we get to 2, and then 0 once we get further on? All right, well,
My guess is make it negative.
yeah, there it is. Okay, so here's how this is going to play out. All right, well, it's t cubed, right? Our function was t cubed, but then we need to turn it off. So we're going to go negative u sub 2 of t times t cubed. That makes perfect sense, right? For once ever in math, it makes complete sense. You want to turn something off? Okay, we'll make it the negative. All right, so this is awesome. We can actually turn things on and off just by using the Heaviside function. So let's go back to the one that I just showed you as a, forcing function for that random differential equation that I was building there. Let's see how we could write that in terms of the Heaviside function. All right, so we had, it was originally, I think it was t sine t and 0. If not, we're going to go with it.
Yeah, it was.
Okay, so all right, so let's think about first, we've got t. Okay, so cool, t. But then something's going to happen at pi. So I'm going to have u sub pi of t. Now let's think about what has to happen. What has to turn on?
The sine of t.
The sine of t has to turn on. So I'm going to turn on the sine. but I also have to turn something off.
The t.
The t has to get turned off. So to turn it off, I'm going to make a minus u sub pi times t. Right? So this was sine of t on. This was t off. Okay. So then we're going to be cruising along again until we hit 2 pi. All right. What do I have to turn on?
0.
0. So I really don't have to turn on anything. If I wanted to, I could put times 0, but I'm not gonna. Instead, let's just think about what I have to turn off. Well, since it's a turning off, let me put those in. I need a minus u sub 2 pi of t, and I'm going to turn off sine of t. So this one just turned sine of t off. So in terms of the Heaviside function, this piecewise function looks like this. Now, the fact that there are 2 u sub pi's, we tend to factor those things out. So you would have u sub pi times sine minus t, and then minus u sub 2 pi t times sine of t. And notice here, the sine t minus t is really doing the on off. Turn on sine, turn off t. All right, well, anyway, so there's the Heaviside function. We're out of time for today, but what we'll see next time is we'll look at, well, what's the Laplace transform of the Heaviside function?
You
And
leave us
therefore,
hanging like that?
of course I am, man. I got to make you come back next week. If I don't give you that hook, nobody comes back.
And he's yours.
Yeah,
It's a
no.
3-day weekend, right? With
I know,
Labor
and
Day?
it is a 3-day weekend. So just some things to remind you. So we will pick this up on Wednesday. All right. But we'll see how we deal with the Heaviside when it comes to doing Laplace and then therefore the inverse. And you'll see why it's way faster tackling one of these problems using Laplace transforms. Okay. But a couple things. So Monday, there is no class. Monday is Memorial Day. So school is closed, which means virtual school is closed as well. All right. I will actually be at a baseball game again on Monday. So it's like perfect timing. I don't have to cancel class. It's great. Anyway, so no class on Monday. Wednesday, we'll continue this discussion. And then Friday is our next exam. As in, like a week from today is exam 2. And I'll go ahead and just tell you right now, exam 2 is going to cover, let me make sure I have the chapter numbers correct. 5-1, chapters 5 through 7. Let me go ahead and write that down here. Okay, so it's going to be chapter 5 through 7, and this is on Friday, which I believe is June 4.
Yeah.
Put a question mark on that because I'm not entirely sure.
It
But
is.
a week from today, there's going to be the next exam on 5 through 7. So all this Laplace transform stuff is chapter 8. So that's not going to be, or maybe even chapter 9. No, I think it's chapter 8, whatever. The Laplace transform stuff is not going to be part of it. Okay. But what will be on it, well, the most recent, so power series stuff, that was chapter 7. The applications, springs, circuits, that kind of stuff from chapter 6. And then chapter 5 was solving these second order things with like undetermined coefficients, reduction of order, variation of parameters. Okay, so that's what the exam is going to be on a week from today. So you can already start working on that a little bit, start studying and preparing. But you know, you still have a week until that occurs. Okay, so no class Monday. That also means the homeworks, I think the next homework sets are due Wednesday. because I'm not going to make them due on Monday. So there'll be homework sets due on Wednesday, and then exam a week from today. All right. So with that, yep, I'm going to leave you hanging. So you're all excited on Wednesday to see how we can just use Laplace transforms to bang that stuff out. All right. So have an awesome long weekend, and I'll see everybody on Wednesday.